All right, good morning. Any issues with ODP 211? All right, cool. So 211, we were building a small tree out of 3 integers, putting it in a function called small. So anything around this should work fine. So there's the node declaration. Order of these fields is critical. We want standard IO to have null. We want standard lib to be able to say malloc. And then our function basically calls malloc 3 times as suggested. Made a trio of nodes, root, left, and right. Those are each pointers to struct t nodes. And then just set them up. So the root has a data value of, RO for root, and the left node is LE, and the right node is RI, and then set up the pointer. So the root points on the left and the right to the left and right nodes, and the left and right children have no children themselves, so their pointers are all null, and then return root, which is the root node. And that basically gets you there. So let's look at the next ODP. If you don't set the children to null, it may work. Valgrind will definitely yell at you loudly. And depending on which system you're running this on, it may or may not work. So always, if you want something to be null, set it equal to null. If you want something to be 0, set it equal to 0. You'll save yourself a lot of heartache down the road at some point. But I don't necessarily check for those things. Okay, so ODP 412. So now you're going to dynamically add a new node to a tree. So you assume that you're given a pointer to the root of a pre-existing tree, okay, and that tree is not null. So the root exists. It's not null. It's actually pointing to a t node, and you're given an integer n, and you want to create a new node to contain n, and then attach it to your tree on either the left or the right. All right, so creates a new node with value n, adds it to the left or right side of the root. So you don't have to traverse down the tree, right? Root is just a root node, and you're just going to adjust either root left or root right to point to your new node, and your new node should have the value n, and its children should be null. So it's almost a subset of what you did in 211. So that opens up in about 75 seconds. So these ODPs open at like 10:05. The root will not be equal to the data value you're adding, because I didn't say what you should do in that case, so don't worry about it. All right, any other ODP questions? What does the return the address mean? It means return root. So root is a pointer to the root node, so just return root. Yeah, because root is a struct t node star, and that's what the function value should return also. All right, so let's go into the details of PA4. We started looking at this yesterday. Let's get through all the details and address any questions on this. This is also the beginning of your 24-hour one-time offer to create your repository on GitLab. Send me an email outside of Canvas, just a plain email, not on the Linux server, just a plain email, and say, hey, can you download my repo? And I will try that for you. I've still got students who are not getting their repo set up correctly. And, you know, in some cases that's been a 0. In some cases it's cost them 40 points. So if you're not, you know, feeling like a risk taker, set up your repo today. Add me as a reporter. Put a README in there. Send me an email. And say, hey, can you download my repo? Okay, that goes until noon tomorrow. I'm willing to do that. So PA4 details, right? So you're creating a database of license plates. There's a database file you can play with, or you can mimic to make your own. That's on the server under /temp database.txt. And you're going to make a program named plate, lowercase plate, and you run it exactly one way. Plate space followed by the name of a database file. Okay, this can be a file in your directory, or it can be, you know, a full path pointing to a database file. And the database file basically just contains the following information. So let's hop on the server again. So it looks like this. It's a bunch of triples. License plate, last name, first name. Maybe it's first name, last name. We'll see what it says. Begin ingesting one line at a time, building the base. The database looks like this. Each line contains a license plate, followed by a space, first name, a space, and a last name, and then a new line. Alright, so you can assume the file I test with will look exactly like this format, but the data will be different. Okay, everything up to the first space is a license plate. Everything between the next two spaces and the last spaces. Alright, do not make any assumptions. Don't assume the license plate is 3 characters, a dash, and 3 digits. Don't assume it's 7 characters long. Don't assume that your name only contains uppercase letters A through Z. No assumptions whatsoever, right? Each line contains a bunch of non-space characters followed by a space, bunch of non-space characters, which is the first name followed by a space, bunch of non-space characters, which is the last name followed by a new line. Alright, so you run your program, you say plate, put in the name of the database file. If for some reason it's not run correctly, if you didn't put in a database name, if you put in more than one command line argument, print out the word error, exit with a status of 1. Just return 1 will do that. Otherwise, program starts running. Open the database file. Okay, you're going to use fopen, you're going to use fgets, you're going to use fclose. Open the database file, read in each line with fgets, which should look something like this, parse it out. You can parse it directly with scanf. Just do 3% s's separated by spaces. That's totally appropriate in this case. Okay, most cases we don't want to use %s with scanf because it ignores spaces, right? It takes spaces as separators, but that's exactly what we want here. So if you just scanf %s, 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 the 3 things that match should be your license plate, the first name, and the last name. Alright, any errors with reading the database, print out the word error once and exit with an exit status of 1. So if you can't open the file, if there's, you know, not 3 things on here, etc., etc. If you find an empty line, error, exit with a status of 1. Alright, you can assume that the plate, first name, and last name are each no more than 40 characters in length. Okay? But when you build your database, you can't just make all of your strings 40 characters. Okay, we'll talk about that in a minute, but you're going to have to dynamically allocate space in your nodes for your tree. But for the sake of reading, you can assume that each of these is no more than 40 characters. So there you can use static strings. You know, make a string plate bracket 41, character first name bracket 41, last name bracket 41, and you can use those as the targets in scanf. Alright, So your program runs, it ingests this information from the database, and as it reads it in, it builds a binary search tree. Okay, the key is license plate. So you're going to use license plate to figure out where you store things in the tree, so comparing to see if you're bigger or less than the root and so on. That's based on plate. The first name, last name just kind of go along for the ride, and they get tacked in with the node along with license plate number. Alright, and then, close the input file, don't leave files open hanging around, and now you basically take commands from the user. And the user can do one of four things. They can type in a license plate, and the program will search for that plate. If it finds it, it will show them the name associated with it. If it doesn't find it, it'll tell them the plate's not found. So that's one thing, look up a plate. Two special commands. If you type an asterisk followed by the word dump, your program will display the contents of your binary search tree, the height, the balance, 3 different traversals of it. So that's a command to look inside and see what your database looks like. If you type *delete followed by a space followed by a license plate, that will remove that plate from the tree if it finds it. Your only other command is Control-D, which exits the program. So unless you type Control-D, *dump, or *delete, assume you're doing a license plate lookup. Alright, when you do a lookup, so I type in a license plate, hit enter, I want to see the following information. First name, colon, followed by the first name. Next line, last name, colon, followed by the last name. I want those on separate lines. Alright, the dump command shows you information about the entire binary search tree that you built up. And so you're going to print out the following information when the person says dump. First you're going to say tree height, colon, show me what the height of the tree is. And we're going to talk about height algorithms. And then balanced, colon, and say either yes or no. And we'll talk about how we determine that. And then 3 traversals, left node right left right node. And for each node that you visit in the traversal, plate, colon, angle bracket, license plate, name, colon, last name, comma, space, first name. Okay, match this format. Do that for the LNR, then do it for NLR, then do it for LRN. Again, we're going to go through all this code today and tomorrow. And just keep asking the user, right? Keep prompting them, enter command or plate. If the person says delete, try to delete the license plate and report either success or plate not found. If the plate is found, you should be able to delete it, say success. If it's not found, just say plate not found. Let's see, question. You said we were sorting these plates via the values of the plate number. Is that the actual number on the plate or the ASCII value? Just the ASCII value as a string. Alright, so exit the program by hitting Control-D at the beginning of a line, free all the memory that was allocated, and then just exit quietly. Alright, implementation. Your binary search tree nodes look like this. There is a plate, a first name, a last name, a left pointer, and a right pointer. So plate, first name, last name, these are declared as just car stars. They're not statically allocated. Right, so don't say car plate bracket 40. You're going to dynamically allocate space for these as you need it. And then left and right are just pointers to more nodes. You don't have to type def a node star, but I'm going to use this in the description. So I've got a node, type def to a struct node star. Okay, there's no sentinel node, so when you begin in your main program, whatever you call your root, declare it to be a struct node star, just set it equal to null. That's an empty tree. Alright, details. So you have a series of required functions that you need to implement, and they need to follow these prototypes. So a height function takes a tree, returns the height. Balance takes a tree, returns an int, which is either 1 if the tree is balanced, 0 if it's not. Add, which takes a root node of a tree, and then 3 strings. License plate, first name, last name. Adds it to the tree and returns the new root of the tree. Search takes a root, plate first, last, and searches for that plate in the tree. If it doesn't find it, it returns a 0. If it does find it, it returns a 1 and also copies the first and last names into these fields that you passed. And then three traversal routines that take a root node of a tree, don't return anything, and just go through and print out the data from each node as described. And then a tree free function, which takes the root of a tree and frees all the memory, including the memory that's been allocated for these strings in the nodes. Okay, lots of moving pieces here. All right, comment block in the beginning of each function. So I want a block that looks like this. I want separate sections that show me the function name, the purpose of the function, a list of inputs, a list of the return, and any side effects. For the inputs, put them one per line. Show me the type of variable, the name of the variable, and a description of the variable. You can add more information on here if you like. Okay, so this is an example of an acceptable comment block for add. Right? So function name is add, purpose, here's what it does. Put this in your own words. It takes in 4 inputs. Here's their names, here's their types, here's what those inputs correspond to. Return, it does return a node, and this is what the node is, and side effects. Alright, and I want that immediately before each function. We'll go back to suggestions and side notes in a minute. Submission, so submit through GitLab in a repo named plate PA4. Pay attention to the casing on this. Alright, make sure I'm a reporter. Put in your .h files, your make files, all of your .c files, a readme if you wanted, anything else that goes along with the source, but don't put in your executables or your object files. Alright, grading, 100-point assignment. These deductions will add up to more than 100 points, but you won't get lower than a 0. Okay, but it's a 100-point assignment. So, GitLab repo, not downloadable by the deadline, that's 20 points off, and then you have 24 hours to correct. If it's not downloadable within 24 hours, that's a 0, end of story. Correctly working make file, if you don't have that, that's 10 points off. It's got to include a clean option, and it should only rebuild what needs to be built based on what's changed. So nice clean make file. I've been seeing clean make files from everybody. Just keep up the good work with those. Okay, if I cannot compile your code, that's at least 40 points off. If I can fix it easily, I'll do so and continue trying to grade. But there's a deduction for that. Any warnings from the compiler when I say make, that's 10 points off. If it's not ingesting the database file, that's half your points right there. If it doesn't handle an unreadable database file, 10 points off. Right? So if it cannot process, you know, a plate first name, last name, you should print the word error and exit. If I don't put in a command line argument, it should print the word error and exit, so 10 points if it doesn't do that. If the license plate lookup doesn't work, that's 30 points. Search tree not built correctly, 30 points. If you use fixed size arrays versus dynamically allocated memory, that's 15 points off. Do you often run into code that can't compile while grading? Oh yeah, way more than you can imagine. Which is oftentimes somebody who, you know, added comments at the last minute and didn't try recompiling because they just added comments. Well, if you put in 1/ instead of 2 for your comment, right, you can't compile. So that's mostly what I see. All right, if the delete command is not working, that's 15 points. Delete is the trickiest function, right? Delete by itself can be a whole assignment. So that's only 15 points if you know, delete totally doesn't work, right? You can still get an 85. I'm going to give you a very specific delete algorithm, and if you don't follow that, it's 10 points off. Okay. If the dump command is not implemented, that's 50 points off. Why? Because without the dump command, I can't look at your binary search tree, right? And your code might be working perfectly, but if I don't have any way to look at what you've stored in your tree, I have no way of assessing, you know, how good your code is other than reverse engineering it. So make sure that dump works. Okay, that's really essential. height function 10 points, balance function 10 points, and those are trivial to implement. We'll see how to do that in the next few days. You're outputting your binary search tree in 3 different orders: in order, pre-order, and post-order, right? 10 points for each of those. That's not coming out correct, so make sure that your orders are correct. Val grind issues or memory leaks, 15 points. Can't exit with Control D, 10 points. If your main program's not parsing correctly, 10 points, right? Unless I type star delete, star dump, or Control D, it should do a license plate lookup. If there's any other behavior, if I hit an empty line and it shows me a help message, right, 10 points off. So only one of 4 things that it can do, right? Delete a plate, dump your tree, exit the program, or try to look up a license plate. So an empty line should generate an error, right, saying plate not found, unless you manage to store a license plate that's got an empty plate number. Output format issues, 10 points. No comment block in the beginning of your main program with name, etc., 20 points. Commenting issues throughout the code, 10 points. Everyone's commenting their code nicely, so keep up what you're doing there. Any problem with the comment block for the required functions, 10 points. Indenting problems, 10 points. Let's see. I've had code that compiles on my PC but not on the server. Yeah, that'll definitely happen. So yeah, always test it on the Linux server. And again, you know, the real acid test, after you've pushed everything to GitLab, go onto the server, completely empty directory, pull down your repo, right, into a new directory, go in that directory and just say make. And it should compile everything and then run your program and do a few of your tests, right? That mimics what I'm going to do when I grade. What do? I make a new directory, I download your repo, I say make, I run it. And the only other thing I do is I go through your code and I eyeball it, right, to look for things in the code itself. But the bulk of the testing I do, you can do yourself, right? And do it at the point where you feel like you're done. You know, everything's submitted, I'm ready to, like, you know, close the door on this whole assignment. At that point, go ahead and do this acid test. Because that'll pick up things like, oh yeah, I forgot I changed the name of the repo at the last minute, you know, or oh, I made that edit to my make file. I should check that again, right? So don't lose points for silly reasons. Lose points for good reasons. You know, you wrote a insert algorithm that, like, you know, collapsed our sun into a black hole. That's a good reason to lose points, right? Don't lose points because, you know, you put a comment in your make file and now I can't compile your code. All right, suggestions. As I said a few times, there are a lot of parts and pieces here. And it can be pretty overwhelming to try to kind of, you know, attack this whole thing that's got, you know, all these tentacles on it and so on. So you want a plan of attack that takes you through a series of manageable steps and gets you to where you're trying to go. So some suggestions, right? First of all, write some code to make a tree by hand in memory. You've already done this in you know, ODP 211 and you're building on it in 212, right? And we did this in class when we first started talking about trees. We just, you know, cobbled together some nodes and said left is this and right is that and so on. So make yourself some trees, right? By taking your node and just, you know, you can start off with statically allocated strings if you want, as long as you remember to change them to dynamic, and copy some strings into them. Right, so string copy. And then you know, look at that in GDB or write a traverse function or something like that. And once you've got a tree, right, you can start using that to develop all your other functions for this. So look at the in-order traversal, right? Left node, right, write some code for that. It's seriously 4 lines of code, right? And if you run that on your test tree, you should see, you know, the data sorted by license plate. Okay, if you've done that, go ahead and do NLR LRN. Right, there are also 4 lines of code. You basically move one line of these 4 from one spot to another. All right, Now do your search function. And search is very few lines of code, right? The way we're going to develop it. And test it, right? So you've got a tree that you've built up by hand. Call your search function, right? Make some static strings first and last. Call your search function. Look for some plate that's in your database, and return result. See if result's equal to 1, and if it is, first and last should have been changed to, the data from your database. Call another plate, do the same thing. Call a plate that's not found and do this, right? And exercise it. There's a side note in here on VI. You can read this. I'm not gonna go even more preachy today, but things like this you can write really easily in VI if you know a few commands. Yank and paste and change word and dot and so on and so forth. You don't have to type all of this in, right? And getting better with VI will help you with all of this. Did you say change word? Yeah. How do you do that? CW. So, alright, quick VI. So, I can come back here, I can just say CW, and whatever I type will replace that word. And if I want to do that somewhere else, I can just hit a dot and it'll repeat that. And you can do DW to delete a word. So if I don't want to do this, or if I want to change that, right, DW gets rid of it. Yeah, don't use replace mode. That's good for very special circumstances, especially when you're doing ASCII art. But DW and CW are nice for working with words, and W itself moves around one word at a time, so that's handy. And B moves back one word at a time, that's handy too. And of course HJKL to move around. Yeah, so I think I've got some VI videos on the CSE website on YouTube, where I go through some of the basic VI commands that might be useful. So if you're curious, go back and look at those. They'll definitely serve you well. All right, so you've built a tree by hand. You've got your search function working. You've got traversals. The next big piece is adding to your binary tree, right? And again, don't get bogged down with your main program. Just make some calls inside main saying add, right? So here's the root of the tree, here's the license plate, here's the names. You just call your add function and get back the root of the new tree, and then call your traversal. And you should see your new tree, your new node appearing in that tree. Once all of that is working, now instead of starting with a tree that you made by hand, start with a null tree. And this is a next level of complexity, but not that much more complex. But this is where you need to make sure you're returning the correct thing from add. So start with your tree equal to null and just call add a few times to add, 3 license plate to an empty tree, and then call your traverse and see if your tree looks correct. What are some common Valgrind errors and how to avoid them? Initialize everything. That is the most common Valgrind error. Right? If you have a node and you want the children to be null, set them to be null. If you're going to use a field from a structure that you just allocated space for, make sure that field has a value because you've given it a value. And Valgrind is there to help you. It's not just there to yell at you, right? If you're not sure, if you're initializing everything, run Valgrind and it'll tell you if you're using something that's not initialized. The other error is memory leaks. That's usually what we do with Valgrind. Valgrind. Almost nobody is getting memory leaks though, which is fantastic. Um, Even when I was seeing, Valgrind reporting warnings and stuff, everybody's freeing their memory, which is awesome, and that's super important. So, but yeah, just make sure you initialize everything. Let's see. So yeah, start with a null tree, call add a few times, and try to build up a tree like that. Once that's working, your add function's working, your search is working, your traversals are working. Now start messing around with the database. Now we're back to a 224 exercise, which is how do we open, read, and close a file using fopen, fgets, fclose. Okay, and we'll review that later on also, but you do some of this in 224, you do some of it in 121. So that's basically, open the file, read in a line, parse it, call your add function. Read the next line, parse it, call your add function. When you're done, close your file. So once that's working, now you can throw a big database of files at it. You can pull down the database from the server, or you can make a subset of it, and you can start testing your code from there. At that point, you can do your height and balance functions, and again, those are a few lines. Once all that's going, make your main program. Right, so what do you have to do? Well, basically you have to deal with the command line argument. So check argv, make sure there's an argument, use that as the name of the file that you're going to open and ingest into your tree, and then deal with user commands. So how do you do that? Well, do an fgets and see if they typed star dump or star delete followed by a string. And if they didn't type one of those things, take what they typed as a license plate and do a lookup. And if fgets returns null, they hit Control D, so you can free memory and exit the program. And then the last thing to work on is the delete function. All right, deleting is tricky, and when you try to delete a node, you can easily corrupt your tree. And if you start, working on your delete function at the same time that you're working on add and search and traverse, and something goes wrong, you have little idea where that problem is. And there's a good chance that add and search and traverse might be working perfectly well, but delete is corrupting your tree. And so when you try to do LNR, it goes into an infinite loop and you think there's a problem with your LNR function, right? So I would leave delete until the end, right? But assuming you're starting this early, that doesn't mean, next Thursday. That means, Monday or something. But leave this for last. And we probably won't get to the delete function until the end of this week anyway. But at this point, you are mostly done. And delete's just another function that you call when the person says star delete. All right. And most important advice, right? Take it in small steps. Take what you know how to do, build up on top of that. Right, and keep testing and validating as you go, so that you don't end up with 250 lines of code that you've never compiled, and now you're going to start doing your debugging. That's a real kind of nightmare scenario. So build up the things that you know how to do, get something running, and then keep embellishing it. That's usually a whole lot more fun than kind of the empty screen syndrome of where do I start, or the 250 line never compiled code syndrome of wow, this doesn't work, I wonder what's wrong. Does that make sense? This is certainly the most ambitious of the projects we've done, and it's intended to teach you about trees and stuff, but also it's a chance to develop your skills further with project management and with breaking things into pieces and so on. When we get to 223, we're going to be doing really ambitious project with lots of parts and pieces and so on, and so you're going to be repeating this process throughout the rest of these courses, right? And certainly when you go on to university, things with lots of different components to them that need to all work together. And so you just want to get some practice with how you're going to tackle that kind of scenario. All right, so let's take a pause from this, and let's play with some tree traversal. Oh, let me show you sample code first. So there's this database file on the server. It's 1,000 lines of randomized database information. So let's just grab a subset. Let's just take the first 5 lines, put it in a database called small. All right, so there's my simplified license plate database. You could make this anything you want. It doesn't have to be license plates, right? It's just some kind of key and then 2 pieces of string data associated with it. So if you want to test it with something else. But let's try this. So temp/plate 4, and I'm going to give it the name of my database. Now, if it's not a database that exists, it says can't open, right? And if I look at the exit status, it's 1. That tells me there was an error. And if I don't put in something, it gives me a usage information. So if I run this with my small database, ask me for a command or a plate. Okay, well, I should be able to type in one of these plates, so let's do OWF 736. And there's Georgie and Thomas. If I do OWF 737, it says plate not found. If I type in anything else, it's going to say plate not found. If I do a dump, it will show me the following information. The height of the tree, well, this tree happens to have a height of 3. Whether or not the tree is balanced, and then the 3 traversal orders. So the left node right traversal should end up being alphabetical by license plate, which it looks like it is. Node left right node are hard to predict. But if you make yourself a tree with some understandable data, you can see if this is correct. And then I can delete. Let's delete the one we're picking on, OWF 736. And it says success. Now if I dump my database, it's only got 4 things in it, and that node has been deleted. And if I search for that license plate, it's not found anymore. And if I try to delete something that's not found, it says plate not found. And finally, a Control D will free the memory and exit. All right, so let's talk about tree traversal. So again, I'm going to work with integers, but the idea is we have nodes of information stored, and there's some sort of ordering to those nodes. Now for strings, how do we compare nodes? Use string compare. And string compare returns a value which is less than 0, equal to 0, or greater than 0. If it returns less than 0, it means A comes before B. If it returns 0, it means A and B are exactly the same string. If it returns something bigger than 0, it means A comes after B lexicographically. So use the result from string compare. Use the sign of that result to tell you when something is to the left or to the right of something else. Well, let's just play with integers again. So how do we parse this? How do we traverse this thing? in left node right order. That's in order. Well, the basic three-step process is first parse the left subtree and then print the root data and then parse the right subtree. So left node right traversal is inherently recursive. The way we traverse this tree is first traverse this, print out a 10, and then traverse that. And if you don't think too deeply about that, it's really simple. If you think too deeply, it's really complex. All right, but how do we traverse this tree? First traverse that, then print the root, then traverse that. That's it. That's recursion. If we wanted to do node left right, how do we traverse this tree in that order? Print that, traverse the left, traverse the right. If you want to do left right node, how do we traverse this tree? Traverse the left, traverse the right, print the root. And the one thing missing here, this only works if your tree has something to traverse. So if the root is null, just return. But assuming the root's not null, go ahead and do this recursive algorithm. All right, so let's do this. So we played around with some insert code a week ago, I think. So sample tree, right, with integer data, left and right children, and we wrote an insert function that went down and searched through the tree and moved left and right and so on. I don't care about that insert function right now. I'm just going to use it to build a tree. So I'm going to call insert a bunch of times and add all of this stuff into our tree. Tree starts off null, and then we just keep calling insert. What I want to do is I want to look at the contents of my tree after this is done. So let's print this in left node right order. So let's call this function LNR on our root. And we have to write that function. But let's prototype it too. All right, so how do we traverse a tree? Traverse the left. Print out the root node data. Traverse the right. And that's almost it. The problem with this is it will segfault because it's going to keep trying to traverse until the root ends up being null, and if root is null, root arrow left will throw a segfault. So I'm going to put in one safety here. That's like our base case. And that's it. That's our whole traversal algorithm. It's 4 lines of code. So if the root is null, return. Otherwise, traverse the left subtree, print the root, traverse the right subtree. That's what LNR traversal means. how do we traverse the left subtree? Well, hey, here's a handy function called LNR. Let's use that. Don't worry about the fact that it's LNR that I'm in the process of writing. Believe in your mind and your heart that LNR will correctly print the contents of this tree. If you believe that, then this is a perfectly functioning statement to traverse the left subtree. And then print the root, and then again, LNR is always going to traverse a tree correctly, so this will print the contents of the right subtree. Well, if I believe that LNR works correctly, then this code should function to do an LNR traversal. So if I make that my LNR function, everything should be hunky-dory. Okay, it's recursive, it's self-referential, it's slightly creepy, it's disturbing, but it actually works. Alright, so we added one line here at the end, LNR root, and LNR root is 4 lines of code. So now that I've done the whole sales pitch on it, let's see if it actually works. I should have compiled it first before I did all that. Alright, so there's the data we inserted, and it's in sorted order. Why? Because that's what LNR does. So one will print the left and right trees. I see the print statement for the root, but not for the left and right trees. Yeah, so this is the key question, right? There's only one print statement in here, and that prints the root. So how did it end up, producing all of this information for the roots of all these other trees? It's a little magical, right? But when I say LNR, the left subtree, right? So I'm trying to traverse this thing. First thing I say is do LNR on this. Well, at that point, somewhere in that LNR of this tree, it's going to print out the root, which is 5. But what's actually going to happen when I say LNR this tree? Well, first it's going to say LNR this tree. And when it does that, it's going to say LNR this null tree on the left, and then print the root of this tree. That's when the 2 gets printed. And then when that finishes and this whole tree containing a 2 has been LNR'd, the left LNR on, the LNR on this tree's left child is done, and now it prints the 5. So it's more than a little freaky, but it's a thing. So yeah, the root is changing. Recursion haunts my binary nightmares. That's like a song lyric, man. That's like really beautiful. It's like a Radiohead lyric or something, maybe. All right, so this is our first full-on recursive algorithm here, but we're going to use something very similar to do insertion, and to do searching, and to do height and balance, and then finally to do deletion. And other than the challenge of, making peace with recursion itself, which is a bit of a significant challenge, but other than that challenge, this is mostly, it's going to feel like you're not doing anything, right? I mean, this code here, we almost didn't do anything. We did one print statement, and then we called this function twice that doesn't exist, until we finish writing it, and we took care of a null root, right? The Turing Dream Machine, I like that. Excellent. All right, so I'm going to leave you with that for now. We got 20 seconds left, but I'll leave you with that for now. So tomorrow, let's look at adding and inserting and searching a binary search tree using recursion, and then we'll look at height function and balance function, and then we'll move on to delete. All right, cool. Have a good one. I will see you next time.